At the forefront of scientific advancement is the European Council for Nuclear Research, CERN, renowned for its groundbreaking contributions to particle physics. Recently, the world-famous particle physics laboratory has revealed an extremely rare finding from its Large Hadron Collider that could completely change our understanding of the cosmos. Scientists believe these strange findings could uncover the presence of alien life in a parallel reality. This groundbreaking idea has sparked excitement and intense discussion among experts. Could this remarkable revelation reshape our understanding of the cosmos? And if confirmed, what profound insights will this discovery offer into the nature of reality itself? Join us as we delve into the recently published findings, exploring how CERN scientists are breaking their silence on this chilling new discovery that has the potential to change everything we know. The European Council for Nuclear Research, better known by its initials, CERN, has been famous for its daredevil experiments since its inception in the mid-1950s. It has been in the limelight several times for good, but its experiments have aroused concern about the potential formation of black holes, rifts in our reality, and many other risks. One of CERN's most famous and controversial achievements was the construction of the Large Hadron Collider, LHC. The Large Hadron Collider is the world's largest particle accelerator. It began operations on September 10, 2008, and remains the most recent addition to CERN's accelerator complex. It spans over 27 kilometers of superconducting magnets and a series of accelerating devices that raise the energy of particles as they go through it. The CERN super invention costs more than $4.5 billion. Many would argue that this money was wisely spent, since the LHC has resulted in some of the most significant discoveries of the last few decades, such as the discovery of the Higgs boson and many other previously unknown particles. This huge machine is capable of speeding different particles around the loop until they reach near light speed and complete more than 11,000 laps per second. The LHC did this with a sequence of very powerful electromagnetics that generates a magnetic field within the accelerator that is almost 1,000 times greater than the field that surrounds the Earth. Some have expressed concern about the impact of creating such a strong magnetic field on nearby electronics, as well as its effect on the Earth's own field. Once these particles reach their maximum speed, 999.99991 times the speed of light, particles going in opposing directions are forced to meet in a violent collision, releasing immense energy and a variety of particles. When particles collide, a stream of particles flees out in all directions, with the majority of them lasting only fractions of a second before fading. Changing the sorts of particles allows researchers to uncover new particles in this flurry. Specially developed ultra-sensitive detectors are installed around the collision sites to record all the information from each collision. This amount of data mounts up quickly and needs a significant amount of time and effort to go through. Every year, the LHC's experiments generate more than 15 petabytes of raw data from these collisions, which must be methodically sorted through to extract the data the researchers want. In 2017, the LHC achieved a significant milestone by permanently storing more than 200 petabytes of data in its tape libraries. To put this quantity of data in perspective, 1 petabyte is comparable to around 250,000 movies. But what exactly are they looking for in all of this data? They detected something going on with a specific type of quark. Quarks are the fundamental building blocks of matter and exist in a variety of flavors, as defined by physicists. Some of these quark flavors are very unstable, decaying into other particles in the blink of an eye. The beauty quark, with an average lifespan of 1.5 trillionths of a second, became the focus of attention due to a specific aberration. Its degradation pattern differed from what scientists expected based on the usual model. According to their predictions, when a beauty quark decays, it will be impacted by the weak force and turn into a set of lighter particles known as leptons. either an electron or a muon, with the standard model predicting a 50-50 probability for both particles. However, the LHC data revealed that these quarks decayed into muons just 70% of the time as they decayed into electrons. This disparity could only exist if a previously unknown sort of particle is involved in the process. This has led some academics to suspect that some new form of physics may be at work. A new force-carrying particle would imply brand new physics that could expand the standard model and answer many confusing questions. The possibility of new physics. The standard model theory provides our best understanding of how the odd world of particles acts. The standard model is a scientific framework that precisely explains every aspect of our knowledge of the physical world's building elements. The astonishing thing is that, despite this high degree of accuracy, physicists are well aware that this model still has to be completed. The standard model only describes three fundamental forces: electromagnetic force, strong force, and weak force. There is currently no description of gravity's force or an explanation for dark matter, the universe's prevalent kind of matter. During recent trials, researchers discovered a discrepancy in the data they were evaluating that differed from what is known about the standard approach. Although it is not rare to find results outside of this framework, given the volume of data produced by the LHC, this time, something piqued scientists' interest, and they saw the need to investigate more to determine this new event. What could this brand new force be? To explain this unexpected discovery, the researchers postulated the existence of a new basic particle, which they refer to as Z prime, a force-carrying particle. Even though this force is most likely extremely weak, because there have been no signs of it until now, the researchers believe it would interact differently with electrons and muons, but the extent of its interactions with standard model particles remains unknown for the time being. If scientists discovered new force-carrying particles, it would be a decade-long awaited breakthrough in physics. Physicists believe that if this discovery is confirmed, it will help to unravel long-standing mysteries of the cosmos and explain age-old issues, such as what dark matter is and the Higgs boson's role in the present day. Some scientists believe that this undiscovered force could help fulfill one of physics' most important goals over the last century: unifying the basic forces of existence. What Elon Musk has to say. According to Elon Musk, CERN built the largest and highest energy particle collider in human history, the Large Hadron Collider, between 1998 and 2008. More than 10,000 scientists, hundreds of institutions and laboratories from more than 100 nations helped with this process. It sits within a 27-kilometer-long tunnel. The boundary between France and Switzerland, near to Geneva, is approximately 175 meters underground. That's not all. The first collision ever recorded at the Large Hadron Collider had an energy of 3.5 tera-electron volts per beam, approximately 4 times that of the previous world record. The energy reached 6.5 tera-electron volts per beam once the LHC was further enhanced. Musk noted that the Large Hadron Collider excels at proton beam collisions. Furthermore, it has the ability to accelerate lead-ion beams in particular. Every year, proton and lead collisions are typically conducted for 1 month. For scientists, testing the predictions of several particle physics theories is the main goal of the Large Hadron Collider. It is important to note, scientists are testing the properties of the Higgs boson and searching for the massive family of new particles, predicted by subatomic particle theories. Hadrons are composite subatomic particles made up of quarks that are held together by a strong force, much as how atoms and molecules are held together by the electromagnetic force. Protons and neutrons are 2 examples of hadrons that are widely understood. Included are the pion and kaon mesons, which were discovered for the first time in cosmic ray experiments in the late 1940s and early 1950s. The LHC brings 2 opposing particle beams together so they can collide. The Higgs boson. The Higgs boson is thought to be an elementary particle connected with the Higgs field. It is the quantum excitation of this field, similar to how you observe ripples in the sea. The boson is like a brand new species in the particle zoo. it lacks the quantum features of fundamental matter and the carriers of quantum interactions, such as electromagnetic force, weak force, and nuclear interactions. The Higgs boson was found at the Large Hadron Collider, a momentous finding achieved concurrently by the two major multifunctional experiments, ATLAS and CMS. It was announced on July 4, 2012, at CERN. At the time, the new scalar boson was discovered primarily in two rare decay channels that provided the purest signal: decay in a pair of photons, which required a totally quantum virtual process, and direct decay in a pair of Z bosons, the carriers of the neutral-weak interaction. Although the finding of the Higgs boson at the time established the standard model, research into this elusive particle did not end there. One of the most significant findings since 2012 was the confirmation of Higgs decay. According to CERN at the time, the research into this elusive particle would deepen during the LHC's third cycle, especially once the particle accelerator's high luminosity upgrade is finished in 2029. This will allow the LHC to undertake more collisions, giving researchers greater opportunity to detect unusual physics, such as occurrences that do not fit into the standard model. CERN estimates that when the accelerator is updated each year, it will produce 15 million of these particles. This compares to the LHC's creation of 3 million Higgs bosons in 2017. This might be useful for identifying various flavors of the Higgs boson. Theories that go beyond the standard model of particle physics anticipate up to 5 distinct forms of Higgs bosons, some of which may be created less frequently than the fundamental Higgs. Even before the improvements, scientists have produced compelling evidence of a magnetic Higgs boson. Magnetic Higgs boson. But what's the big deal about the Higgs boson? This Higgs field was incredibly significant and critical in the early times following the universe's creation. It dictates the very nature of the vacuum that exists in our space-time. It is what causes matter and interactions to exist as we know them, as well as the emergence of mass in all known fundamental particles. Without the Higgs field, and consequently the Higgs boson, the cosmos would be devoid of atomic elements, stars, and life. Why do you think the Higgs boson is called the God particle? Popular media helped cement the Higgs boson's nickname, the God particle, after its discovery. The genesis of the term is commonly traced to Nobel Prize-winning scientist Leon Lederman, who, in anger, referred to the Higgs boson as the goddamn particle, since it was so difficult to detect. According to Business Insider, when Lederman authored a book about the Higgs boson in the 1990s, he wanted the title, The Goddamn Particle, but the publishers disagreed and changed it to The God Particle. That was the beginning of an issue between the particle and religion that continues to concern modern physicists. Nonetheless, it is difficult to overestimate the significance of the Higgs boson and the Higgs field, because only particles would have mass under this aspect of nature. That implies there would be no stars, planets, or humans, which may help explain its bombastic nickname. Aside from the apparent need to accurately characterize the new particle, scientists continue to research the Higgs boson for two reasons. First, they want to know how the physical vacuum in which we dwell originated in the early cosmos. Second, they want to know how this physical vacuum can be kept steady. The Higgs field is peculiar in that it transmits non-zero mean anticipated potential energy to the physical vacuum. Essentially, this is what makes all the difference in our cosmos. Scientists think that accessing the form of the energy potential is accountable for the presence of the electromagnetic force with a limitless range and the weak force with extremely little range. To do this, scientists must investigate how the Higgs bosons interact with one another. And for that, they must create pairs of Higgs bosons. The Higgs boson contributed to the answer to the critical question of how all other basic particles get their mass. However, its bulk is yet to be explained. Any symmetry in the theory does not safeguard this mass and causes unintended instability. Quantum fluctuations might disrupt the physical vacuum itself. Fortunately, this is on timescales much bigger than the universe's known lifespan. but scientists are still seeking for extra Higgs boson-like particles that would indicate the presence of the new physics required to stabilize the Higgs boson mass. All these considerations encourage the study of significantly more data and, if feasible, access to greater collider energy. This is why 10 years later, hundreds of experts throughout the world remain committed to the effort. The Higgs boson was first proposed in 1964 and found in 2012. Science aficionados have questioned why it took so long. It's because the Higgs boson is both massive and exceedingly unstable. To create such a massive particle, scientists had to concentrate a large quantity of energy in a small container. They required a high-energy collider. Once formed, Higgs particles break apart in a variety of ways, with just a small proportion detectable from the background. Scientists built the largest and most complicated detectors to identify such particles. Then, they investigated hundreds of billions of proton-proton collisions to find a Higgs boson signature. However, will CERN's projects and findings enable us to make big discoveries? Will it send us to our ultimate demise? Conspiracy theorists have three main hypotheses about what CERN is actually up to. The first and deadliest notion that has caused some to point fingers at CERN is that the organization is attempting to open a portal to hell. Some believe that CERN's experiments with subatomic particles flying at the speed of light will carry humanity beyond the gates of the final inferno. However, CERN has said that the goal of generating antimatter is to better understand matter and mass. Wikipedia defines antimatter as subatomic particles having the opposite electrical charge of matter. Supporters of the Big Bang Theory believe that antimatter was formed during the universe's origin and should be represented equally with matter. However, antimatter is extremely uncommon. The second CERN conspiracy hypothesis surrounds the Mandela effect. The Mandela effect is a phenomenon in which many people recall a prior event differently than it really occurred. Some conspiracy theorists believe that CERN's particle experiments will trigger disruptions in our reality and propel our planet into another realm, resulting in a large-scale Mandela effect. Finally, some conspiracy theorists think that human sacrifice takes place on site at the CERN facility. A video allegedly leaked online in 2016, stating that ritual sacrifices were taking place at CERN. The footage purportedly depicted several hooded people going around the CERN campus. It was thought that the tape showed a little girl getting stabbed in the chest by the masked people. According to The Guardian, a CERN spokesman stepped out to debunk the story, claiming that the ritual was staged as part of an elaborate joke. The question of whether a police inquiry took place after that is yet to be resolved. It is no surprise that CERN has long been the focus of conspiracy theories. As a result, it's not surprising that on July 5, 2022, when scientists began operation after 3 years of improvements and maintenance, conspiracy theories would emerge online. While scientific enthusiasts may be disappointed with this revelation, it is apparent that CERN has no ambitions to build a doorway to hell, the future, or any other dimension. Ghost particles detected. Proton beams continue to zip around the 27-kilometer circle of the world's biggest particle accelerator, which is located over 300 feet below. For almost a decade, its capacity to smash particles together at extraordinarily high energies has allowed humanity to see into the unknown frontiers of physics. FACER, the LHC's forward search experiment detector, has produced an unexpected result. For the first time, it identified high-energy neutrinos produced by a particle collider, identifying 153 neutrino interactions with exceptional accuracy. This huge milestone in particle physics might help scientists get a better understanding of the universe's highly intense neutrino interactions, as well as uncover the mysteries of how stars burn and burst into supernovae. Neutrinos are small subatomic particles that exist practically everywhere. Neutrinos are created when atomic nuclei join or break away. They are formed by cosmic rays and radioactive decay in Earth's particle accelerators and nuclear reactors, as well as the natural radioactivity of potassium in bananas. However, these massless and chargeless particles represent the ultimate cosmic ghost. Once created, they seldom interact with matter. Every second, around 100 billion neutrinos travel through each square centimeter of our bodies, but they are so elusive that we cannot feel them. This mysterious characteristic gave them the nickname ghost particles, and scientists have been hunting them since 1956, when they were first detected zipping from a nuclear reactor. Physicists discovered the traces of 6 neutrinos in 2021, but it took them 2 years to gather enough evidence to prove that these ethereal particles were genuine. According to James Boyd, a particle physicist at CERN and co-spokesperson for Voyager, ghost particles can teach us about deep space in ways that other methods cannot. These extremely high-energy neutrinos at the LHC are vital for understanding appealing particle astrophysics findings. The project will continue collecting data until the end of 2025. Scientists anticipate discovering more of these ghost neutrinos and revealing physics mysteries that we have yet to investigate. Scientists are waiting with bated breath to see what CERN will uncover next and what the next discoveries will mean for the future of science. Thank you for watching another episode of Voyager. While you are still here, click on the video on your screen to see more mind-blowing videos like this one.